The current technology for processing of natural gas liquids consists of a train of distillation columns as pictured here, a demethanizer, a deethanizer, depropanizer, debutanizer, a C4 splitter, and this distillation train is able to produce purified methane, ethane, propane, isobutane, normal butane. In this presentation, we consider an alternative to the use of a distillation train by using pressure swing adsorption technology and a metal organic framework. In theory, any zeolite, morph, or adsorbent should be capable of separating methane from ethane and propane and higher hydrocarbons on the basis of the differences in the London van der Waals interactions. The London van der Waals interactions consist of the sum of the attraction and repulsion forces that are usually expressed in this form, where r is the distance between the adsorbate and adsorbent. The forces of attraction and repulsion are proportional to the polarizabilities alpha of both these adsorbate and adsorbent atoms on the surface, and the polarizability increase with the size of the molecules. The expression for A and B are provided here, where C is the speed of light, G is the magnetic susceptibility. It is very common to write the London van der Waals interaction in terms of Lennard-Jones 612 potential. It is interesting to note that despite what the name London might suggest, Fritz Wolfgang London was actually German. Johannes Dietrich van der Waals won the Nobel Prize in 1910, and he was a professor at the University of Amsterdam, where I am also located. The polarizabilities of linear alkanes increase with the size of the guest molecules, and I show here the data for methane, ethane, and propane. For background information, consult my paper in ACS Omega 2020. Watch also my video presentation on adsorbate-adsorbent interaction potentials on my YouTube channel. Let us restrict ourselves to a feed mixture consisting of methane, ethane, and propane, and let us look at the choice of the morph that results in higher productivity of purified methane. Depending on the choice of the morph, there are various possibilities of the hierarchies of adsorption strengths. I consider two cases. This is taken from figure 1 of the paper online in the AICHE journal. In this case, we have a high selectivity of C3 with respect to C2, but in this case, the productivity of purified methane is restricted because the methane purity is dictated by the breakthrough of ethane. So we would like a MOF for which methane breaks through almost immediately, but the breakthrough of ethane is delayed to a much later time, such that a higher productivity of purified methane can be realized. Indeed, we need to have a MOF with a higher ethane-methane selectivity, and we need to have a MOF for which the C3-C2 selectivity is as low as is possible. So there is a subtle optimization task that we have to accomplish. In the paper by Chen and others, as reported in AICHE journal, the optimal MOF for purification of mixture of methane, ethane, and propane is TIFSIX-Cu-TPA, and the isotherm data and the data on isosteric heats of absorption show that there's a large difference in the adsorption strength of methane and ethane, but the differences in the adsorption strength of ethane and propane is very small and limited. This is the scenario that results in the higher productivity of purified methane. The breakthrough data for a mixture of methane, ethane, and propane confirms that a record productivity corresponding to 5 moles per kilogram of 99.99% methane can be recovered by use of TIFSIX-Cu-TPA. Here we show breakthroughs at 2 different flow rates. The separation performance is practically uninfluenced by the presence of water in the feed mixture, up to 80% relative humidity, and the breakthroughs for 4 different cycles are practically identical, leading us to conclude that TIFSIX-Cu-TPA is a candidate for natural gas purification.